David, take it away.
Awesome. Thank you very much. Everyone hear me at the back? Okay. Yes. Okay. Excellent. It's nice to be back at U of T. It's fun to come back and visit and be back in Toronto. I'm going to be talking to you today. Apologize in advance. This is going to lean more towards the computational side than the mathematical side. I know everyone here likes math, but hopefully there's something interesting here for everyone. I'm going to be talking about how sort of a new mechanism for explaining the high variability in cortical spiking, which relies on metastable cluster dynamics. I'll get into what that is in a second. And this is work that I've done with my supervisor, Luca, and another postdoc, Leah, in our lab, who came up with the model. So highly variable spiking. Obviously, I think everyone already knows this, but cortical neurons display highly variable spiking, and we tend to categorize, or we measure that with the Fano factor of the spike counts, the variance of the spike counts in bins divided by the mean. If that's greater than or equal to 1, we say that's highly variable, and that's what's observed in cortex. I should say I'm talking mostly about spontaneous activity, not evoked activity, but it's seen in evoked activity as well. Now, the classical model that explains this uses EI balance, this idea that you have lots of inputs, but you're balancing out the excitatory inputs and the inhibitory inputs, leading you to the fluctuation-driven regime. You get this highly variable spiking. Unfortunately, there's a sort of growing body of evidence that some of these predictions of that fluctuation-driven regime aren't seen. So there's sort of an unrealistic assumption of complete asynchrony, and the membrane potential varies a lot less than what we actually see. I should note that neither of these is like a nail in the coffin. No one is saying that, oh, you can't possibly have EI balance in the network and it can't contribute to this variation, but it does ask the question of, oh, okay, there's been some formatting changes. I apologize for that. But it asks the question, can we find a new mechanism that might explain this as well, that might be playing a role? And so there was a recent study, this one, again, I apologize for the formatting changes. But a recent study found that highly variable spiking can actually be explained by synchronous activity in neural inputs. And so this is a good study. They do all sorts of things. They took a look at in vivo measurements of activity and of conductance inputs, and they then did some in vitro experiments where they tried driving these neurons in different ways and seeing the outputs, and then they had some theoretical work as well. And what they found was that, first of all, there is evidence of the synchrony, so the synchronization between units. And I should say this isn't anything crazy. It's just basically a low level of correlation between all the inputs across the network, so some sort of time-varying instantaneous rate that is common amongst a large group of inputs. And so this is sort of weak correlation, but spread out over lots of units has a big effect. They then show directly that these synchronous inputs can produce highly variable spiking without EI balance. And lastly, they show that you can actually, they show this interesting result where you can scale that Fano factor above 1 by changing the time scale of the synchronous activity. Okay, so what that was supposed to say is basically that all of this was very good, but they're basically looking at a single neuron response to various inputs. They don't have a mechanism for how the cortex produces this synchrony in the first place. So that's where we're going to come in. We're going to introduce a model that can reproduce all three of these results. And so our model is relatively simple. We employ a model of clustered leaky integrate and fire neurons. So the clusters look something like this. So you can see here's a model with 18 clusters. So here are the excitatory units. Then they're much more strongly connected. This is the weight matrix. They're much more strongly connected within their little clusters. And the clusters also include some inhibitory neurons as well. And the nice thing about this is when it's under spontaneous activity, we get this very interesting dynamics where the clusters will turn on and off between the on state, which is a high firing rate, and the off state, which is a low firing rate. And the switching is, just completely spontaneous. It'll just randomly fluctuate between each of these sort of metastable states where different collections of clusters are on or off, as shown in this raster plot here. Similar models have previously been shown to display this highly variable spiking, and what we're going to show is that they also reproduce these synchrony results that were found in this paper. So this is sort of first hand-wavy evidence. If we take a look at just one cluster, and we look at the input current to one neuron in this cluster, so this is just the net postsynaptic current going on in this neuron, we can see that it very obviously correlates with the activity in the network. So it is seeing the synchronous activity of all of the neurons within the same cluster. So this is sort of hand wavy, but what we want is actual good quantitative evidence. We're going to follow that paper, and what they did in their experimental studies is they looked at something which they call Q, which measures the mean of the excitatory postsynaptic current versus the variance of the excitatory postsynaptic current, and then they divide by the synaptic timescale. And the nice thing about this is that, okay, for if you have independent Poisson inputs with weights J and rates R, what happens is you get this very nice formula. So this is assuming independence. This is assuming no synchronization between your units at all. You get this nice formula. And if you then assume that your weights are roughly uniform, it simplifies down to just K, which is the number of inputs times the average rate. And what they said is that if you find experimentally that Q is much less than this prediction, that's effectively saying that your number of independent inputs is effectively lower than the true number of inputs. Or in other words, your inputs are not independent, and this is what gives them the evidence of their input synchrony. And so we can do that with our model. So here's the plot. We have here our calculated Q ind. We also have a pointer. I don't know why I'm pointing with my hand. I have a pointer. They have, or sorry, I've done this numerical calculation where we rerun the simulation, but we replace all of the recurrent spikes with random Poisson noise. And that is over here that just makes sure that our calculation was correct. And then we have the actual measured value for our model, which you can see is much, much less. We have this nice gap, and there we have our evidence of input synchrony. It would be nice to get a number for that synchrony. We're working on that calculation as we speak. But there is the first result. Second result, we want to test if we can now ignore EI balance. So the way that they do that, and the way that we're going to do that, is we're going to take our recorded excitatory and inhibitory currents, and we're going to drive our neurons either with both the like the total drive, the total current, or just with the excitatory current, and compare those two. So this is the original. This was what was seen in our model. We know this is highly variable spiking, but can we also get highly variable spiking with only excitatory inputs? And what you can see is that you do. So here is our plot of the Fano factor. So this is the line 1. So we want everything to be greater than this. And we can see that we get that both with the balanced or the more balanced drive that includes the inhibition, as well as with the excitatory only drive. There is a reduction, but it is still highly variable. I should say there's a couple caveats to this. The first one is if you're going to compare Fano factors, you need the rates, the overall rates, to be roughly similar. And you want to avoid issues of saturating your neurons. So we did have to turn the gain down on the excitatory drive for the E only case. And then the other issue might be that here we're only looking at the excitatory clustered population. This is something I'm still investigating in the model, but for all of the other populations, so in particular the inhibitory population, the Fano factor is below 1, but it's below 1 in both cases. So we didn't include that in our comparison. So just to recap, we're looking for evidence of synchrony in cortical inputs. We're looking for evidence that those synchronous inputs can produce highly variable spiking without EI balance. We have both of those, and now we need to look at whether the Fano factor scales with the time scale of synchronous activity. So to change the time scale, so we need a way to change the time scale. Luckily, we have that. So this model was originally designed to look at arousal changes in the auditory cortex, and we can reuse that handle to change the time scale of our cluster dynamics here. So what happens, or what we do is we decrease the recurrent connections between excitatory units, and we actually increase the external Poisson noise. And doing both of those things together will decrease the time scale of our cluster dynamics. We can then extract the cluster dynamics. What we do is we take the autocorrelation spectrum of our input currents, we average those together, and we fit with an exponential to extract a time scale out of this. And so you can see that at low arousal, which corresponds to this, like at the top here, we get a longer time scale. And then as we move down, we get a shorter time scale, as you'd expect. And if we compare this against the Fano factor, the average Fano factor of all the units in the models that we're looking at, we see a very good agreement with the experimental results that were collected in the paper. The experimental results, what they did, I should explain that a little bit, is they took a statistical model that produced synchronous spiking with a particular timescale, and they produced a what do they call it? Like a simulated input population of spikes, and then they fed that into a sort of an in vitro setup and looked at the Fano factor that resulted from that. As you can see, that we reproduced these results very carefully. We thought this was very exciting. This is actually the first result we got that prompted us to keep looking for more agreements between our model and the paper. So there's still a bunch of next steps to do. This is still preliminary work. We're looking at optimizing our model parameters. We want to see if we can tune the level of synchrony and the timescale of that synchrony separately to see how much of that phase or how much of that parameter space we can carve out. We want to compare against more experimental results. In particular, we want to compare against the membrane potential variability and see if we can produce the increased variability in the membrane potential that's seen away from the fluctuation-driven regime. We have some preliminary results that show that that should be true, but we're looking for a good data set to compare it to. And then finally, we're looking for anatomical correlates for clusters. What structures correspond to our clusters in the cortex? So if anyone has any experimental data that they think would be, or results they think would be cool, or if you have, anatomical data that could, lead us to finding these clusters, please come find me. I'll be at the poster sessions. I'll be around all week. So I'd love to speak to you. And then finally, in conclusion, these preliminary results suggest that these metastable cluster dynamics could be the self-consistent mechanism behind both synchrony and the highly variable spiking in the cortex. So I want to thank my collaborators, and I want to thank all of you, and especially the organizers, for letting me speak here today. Thank you very much.